Okay, good afternoon. You are welcome to the 536 High Speed Dynamics video, video lecture. Today is the 20th. Sorry, 30th of January 20. So the course, as we discussed before, is going to be based on modern compressible flows with historical perspective. The textbook, second edition of the textbook, written D. Anderson. The slides which I'm going to be showing have been made from the textbook. So most of the material is from the textbook. Introductory thoughts. You've done aerodynamics before, incompressible aerodynamics before. In discussing about incompressible aerodynamics, we said that incompressible flow is a flow in which the density remains constant or is assumed to be constant. Addition of the definition needs to be done. In real life, all flows are to a greater extent compressible. It just now depends on how much you want compressibility in the flow to affect results which you want, how much you think the compressibility effects might affect results of any calculations we are making. So incompressible flow is more appropriately defined as one in which the effects of the change in density seem to be negligible, because in actual fact we can't 100% compressible flow. And to bring that to life, I'm going to share more on app. It's a kind of app. I don't think it's an app. You can also visit the website and try to see that URL there. I think it's some kind of app on NASA government website, and it uses the various length scales of matter in the whole universe. So right now in this kind of length, we have human beings. You can let's try to read what's written there. So the explanation: what does the universe look like on a small scale? So on large scales, humanity is discovering that the universe is a very different place on every proportion that has been explored. For example, so far as we know, every proton is exactly the same, but every huge galaxy is different. On more familiar scales, a small glass tabletop human being is a vast plane of strange smoothness to a dust mite. As you get we're talking about now, with the app, we're just going to be the different kinds of skills that we have. We have the macroscopic scale, which is the kind of scale that we as beings we can see with our naked eyes, and then we have the microscopic scale, which we can't see with our naked eyes unless with the use of very strong microscopes. In the app, that the particles of fluids, particles of solids, they are all on the microscopic scale, those that we can't see with our naked eyes. So we are going to try to see, from chemistry that all gases or all kinds of matter are made up of electrons, protons, molecules, and all that. So we're going to try to use this app to have a kind of real feel of how things really come about, or maybe how they really are. So if we use scale here, we see that a human scale, that means macroscopic scale. Of course, you can see a giant earthworm without the use of a microscope. You can see the duck there without the use of a microscope. When we were to go like further into a step further, of course, we can still see a hummingbird there, but hummingbird is very, very small. The max it is very small, smaller than the basketball or on this scale. We go there even further, and then we can see an ant there. Some of the ants are very small, very small. They seem very tiny, but you can still see them. That means we are going from the very macroscopic to microscopic bit by bit, and then over there, um, something of salt, so a grain of salt. You see, as you feel that the salt is just in powder form. If you take just any part of a single grain, that's on the scale it is. So the scale of an amoeba, mite, and all. So we are going into the scopic scale, and you see the thickness of paper. You see how it's in relation to the grain of salt. So, and even we are still not on the very, very microscopic scale. We are not on the atomic level yet. We still have to go further inwards. So we keep going further inwards. So this is of interest to me here. The mist droplets. Mist is just EV. Those tiny droplets are mist droplets. So, of course, it's made up of water. So the mist is we start talking about fluid elements in compressible flow. You liken such an element of fluid to the mist droplet. So to better understand the behavior of the fluid and then the mist droplet, to try to delve in more into what exactly might be inside the mist droplet. So I'm going to go further into the microscopic level beyond on which the mist droplet is. So we see that we can still find things that are smaller than the mist droplet. So we go further. We are not even on the atomic level yet. So we go further and further and further and further, and we get to the atomic mist droplet. Droplet it's a microscopic level. It's you might not even be able to see mist droplet. When compared to the atomic level, we see that it's like a very huge volume, because in a mist droplet we have millions, and only God knows the amount of molecules and atoms of hydrogen and oxygen, to be precise, water molecules contained inside the mist droplets, all going around inside of motion. molecule is even bigger than atoms. In a mixed droplet, which is just in a mixed droplet, which is very, very comparable to the fluids we're talking about, we have means uncountable number of hydrogen water molecules, that is, in two hydrogen atoms with oxygen all together. So we have all this moving all around. That's what a fluid feels. And we know that water, solids, liquids, and gases are different just because of the kind of interaction, molecular interaction that is in between molecules. For such, the molecules are tightly bound together with very strong intermolecular forces, which is solid rigid structure. For liquids, the molecular structure is less rigid. The intermolecular forces are not as strong, so the kind of fluidity that comes into play for this, that means the molecules, this is like a single water molecule. It's tightly bound. If this were like the mist we are looking at, we would have some other water molecules all around. The forces put together are not so strong, so each of the molecules have the ability to move, slide about the other ones. And for the intermolecular forces are even very, very weak. So if there's some gas, or if it were what we call the water molecules all around, be held together with any kind of strong force. So what comes to mind now is the concept of density. That means in a given volume, how much of this kind of molecules do you have? So for solids, of course, the density is so high because you have so many molecules densely. I'm still using the word density. You have so many molecules put together to a very, very small volume. When it comes to liquids, the molecules that are put together in a given particular volume, many are have in a very dense solid. So the density of liquids are usually lower than those of, and when I want to compare with gases where the molecules are all around, we see the density of gases are less than those of liquids and solids. What we should note here is the fact that the molecules in gases have spaces to move out in, means if there was some kind of way we could close up those gaps in between them, we need to we'll be able to increase the density. That's what we mean by compressibility of a gas, because the space between the molecules are enough spaces between the molecules, so there's still enough room to keep putting more and more molecules together. That means you can be closing up the gap if you apply as much pressure. As you are closing it up, density will be changing, it will be increasing. As you are releasing the territory you are using to compress it, of course, the molecules have more space to move around in, and then the density decreasing. What here is the fact that with the application of any kind of pressure, you can be closing up the space, decreasing the volume, the density will be changing. If the force is modestly released, then the space becomes bigger, and the molecules have so many space or much space to move about. The density is always changing with any kind of flow. So, an incompressible flow, is a mix. But if it is changing on this very, very small on the atomic level. We might not really consider or not be really concerned about such very small changes in density. However, changes in density is so much because the pressure bring about such changes is so high, or the pressure change bring about such changes in density is so high. Of course, density might now be quite macroscopic, and if the effects of such changes in density are not taken into account, then it could lead to errors in calculations. So if we now go back to slide and continue discussion. Most of liquids and low speed flow of gases fit into this definition. Liquids, as I've tried to explain, fairly incomplete. The space the molecules are not as much as you have gases, but there are still some spaces. That's why the liquid molecules can flow over others. So if you have much force, you can still kind of like close the gap, but you so much force to even make any appreciable of the gap. So usually on the macroscopic level, liquids can be thought of as being or the flow of liquids can be thought of as being incompressible. And that is when the speed of the flow is not as strong or as fast. You don't have as much pressure changes to bring about the much change in density that would bring any kind of error into calculations if it's taken into account. The dynamics programs of the 18th, 19th, and early 20th centuries are almost always involved, or almost always involved low speed flows of gases. So they were incompressible flows. So the first Bernoulli equation, which you experimented about, was then you do P plus half root V squared equals constant on a streamline. That means we do P1 plus half root V1 equals P2 plus half root V2 squared. You are just assuming that as you move from one on the streamline to the other, density remains constant. But I have to explain to you that you can have very, very little variation density, but for when the flow is that much speed, then the two variation might not bring about a much changes on the macroscopic level that might be considered some kind of error if those changes were not into account. So in high flows, the Bernoulli equation in the form that it is written in 1.1 accurate. In 83, the Swedish engineer Carl Dolaval exhibited the steam turbine engine, and the steam turbine was driven by high speed, of course, steam being fed into the blades, and the action of the high speed steam treated the blades at so great a speed that I hadn't ever seen before. Then that flow wasn't compressible. Of course, it's the compressible flow of steam, and that's the way for the design and operation of supersonic wind tunnels and engines and all that in later centuries. And by 1947, the first aircraft had been designed, and Captain Charles Chuck Yeager, that's his name, faster than the speed of sound. Let me try to take a picture from the internet. Yeah, so you can see the name better here. The first player flew faster than the speed of sound. So the one of the things of flying faster than the speed of sound with the bed X of X1 was to add new, if like the new classification of flows, then flows. Such kind of flows include the internal flows through rockets, gas turbine engines, high-speed supersonic, transonic, supersonic, hypersonic wind tunnels, and usually once the Mach number is greater than 0.3, then you assume compressible flows. So by having the definition of a compressible flow, of course, in the layman language and just the words, we say compressible flow is a variable density flow. So we'll explain then if you consider a small element of fluid like the droplet, the volume, I take the volume to be V. Then you can define the compressibility of mist droplets out as tau, and then when it's like that, some change in the P, some change P over the surfaces of the mist droplet. That means we know if there is some pressure imbalance, you have some kind of flow. As the pressure is reducing, the static reducing, dynamic pressure is building. That means once the static pressure is reducing, you have some kind of flow, because the dynamic pressure is increasing, or if you have some kind of dynamic pressure, that means you have some velocity. So when the static pressure is reducing, or maybe when there's some pressure imbalance somewhere in the fluid, bound to have some kind of flow. So we are now going to define compressibility based on some kind of change in pressure, the P, and the consequent in fractional change in the fluid. But when the pressure is increasing, when you are increasing the pressure, or say the mist droplets, you are cooling up the volume. That means the volume will be reduced, and that is why there's a negative sign. So we define compressibility of the fluid as negative fractional change in volume by the change in pressure. So meaning that after you might have compressed it, or after it might have gone through some kind of compression, the volume have then you subtract it from the previous volume and then divide by the previous volume, just as that written there. So that's when you are compressing some gas. If you want to experience this better the next time you go to fill in your gas cylinder, you can trace. When the gas is being filled, of course, you put your hand around the cylinder, you feel that the temperature is going up. So, of course, by increasing the gas, you have to put in so many molecules into a confined volume. The molecules which are moving around with so much kinetic energy will now be confined into a a much more confined space, and molecules will keep bombing the um, uh, the walls of the cylinder. They are acting their kinetic energy on the walls. Impacting their kinetic energies on the walls, they are transferring such energy in form of heat. So that is why you have the temperature around the around the walls of the to be going up. So you can have the definition of the compressibility in two ways. Thermal compressibility, which has tau sub T, the fractional partial derivative of the partial derivative of volume with at constant temperature over the volume. When the molecules, like in the case of compression gas that I was talking about, when the molecules are bombarded of the container, the energy to the walls, and then lose from the walls, the energy is transferred to the environment. Once they lose energy, the kinetic energy reduces, and the temperature reduces. The temperature of the fluid also reduces, but you are still compressing and compressing. So actually, the temperature should be getting higher. But because the molecules are losing their kinetic energy from the by bombarding the walls, and the energy transfer from the walls to the surrounding, there is because there is constant transfer of energy from the molecules as they are compressing them to the surroundings, the temperature will be kept almost constant. You have the isothermal compressibility. So we know that when you are compressing some gas and you allow the gas to be losing energy to the surrounding, and the temperature is to be fairly constant. So you have the isothermal compressibility defined there. You can have a system whereby when pressing the gas, you are not allowing the energy, the gas to be lost. That means you insulate the walls of the container, so the energy of the gas, the gas processed before compression is conserved. It's not transferred. You have some adiabatic compression. When you have adiabatic compression, that means there's no heat transfer, so loss in energy. And the compression takes place without any other kind of dissipative phenomenon like viscous effects. Then the process will be reversible, and the isentropic process is one which is both adiabatic and reversible. So we can then define the isentropic compressibility as how S equals minus 1 over V partial derivative of V with as we know from intuition, the compressibility of liquids are very low compared to those of gases. So in terms of density, the compressibility is given tau 1 over rho dp, and this is because this will rho the inverse of volume. So rho v is 1. So we decide to take the derivative equation using through, we know that that will be V d equals 0, because the derivative of 1, which is a constant, is equal to 0. So you need to say that V will be equals rho V. We can separate the variables to have the mass dV. So if I write tau equals, if we write equal minus 1 over V del P, del V, then we can substitute in rho del over rho minus del V over V, and that's what we have. They have over rho del P. How come we have 1.5? Quickly we see that the change in pressure is just equal to the density of the fluid times the compressibility of the fluid times the change in pressure. I mean, the change in density equals then the previous density, initial density times the quantity of the fluid times the change in pressure. You see, large gradients usually create large value gradient. That means when you have so much gradient, you expect to have so much velocity gradient. That means you expect to have so much velocity changes. So that means when you are considering a very high speed flow, you know that there are so much gradients of pressure. If was to be a very high speed flow of liquids, you know, liquids have very, very low values of compressibility. So that's the change in pressure, the change in density means even you have a very large change in pressure, of course, the compressibility of the fluid is very, 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 very low. Then a large change in pressure does not give you that much change in density. But gases, gas considerably high values of compressibility. And it's when the pressure gradient is quite large, you can have corresponding change in pressure, also change in density, which is high as well. So when density is changing, immediately we can see that Bernoulli's equation is done, because Bernoulli's equation says P plus half rho squared equals constant. That if cement when on a streamline like that, I have to know I know the pressure here, and then and pressure here, P2 here the pressure is P1, and then at this second the pressure is P2. The P2 velocity here So I don't know what the velocity there is. So if this were those flow, like incompressible flow, I can apply Bernoulli's equation and say P1 plus half rho 1 squared equals loss rho V2 squared. So for the discussion now, let me name the density as rho 1 and the density there as rho 2. For 2 for V2 equation, that I need to know P1, which I've just probably I know now. I know V1, I know the density, the value of the density here. Let's say it was given as well. And then I need P2. I said given, I need to know rho 2. I need to as well. If a low speed flow, I can just assume that rho 1 should be equal to rho 2, that shouldn't be changing density. Then I can just use the value which was given here for all of the density there, and then I can calculate for V2. But if you now have very if the flow is so high, the density has changed so much from there to there, then rho 1 will equal to rho 2, and if you use the noise equal then. So we need to now find other means to such flows. So find a compressible flow as compressible flow will be considered as in which the change in pressure dP over a characteristic length of the flow multiplied by the change in pressure dP over some characteristic length of the flow multiplied by tau, and the density multiplied by tau results in some final change in that is the rho over rho, which is just too large to be ignored. So for practical problems, if the changes by 5%, or the flow is considered to be compressible. So the much more technical way discuss or describe compressible flows. So next we'll talk about flow regimes. We know that, of course, you are familiar with subsonic, what subsonic flow is, you know what flow is, supersonic flow and hypersonic flow. So I'm going to quickly brush over them. You have flow properties like pressure, temperature, density, velocity, point properties. Now vary from point to point within low field, so that the value of pressure or temperature at a point A in the flow field may not necessarily be the same as the value of temperature, pressure, whatever there will be in another in the flow. So the speed of sound, which is directly related to the of the medium, is also varying within the flow field, so that the low Mach number being the ratio of the speed of objects over the speed of sound, will also be varying at every in in the flow. Hence, we find flow regimes which is drawn in figure 1.3 of flow, in which the mass is less than 1 at every point in the flow field. That means at not with any single point is the speed of the Mach number equal of sound. When you have Mach number to be equal to 1, that means the speed object or the free stream speed is equal to the speed of sound. Then also a sonic flow, of course, is then a flow in which the speed of the object is just, or the free stream velocity is just equal to the speed of sound. A transonic is one which the characteristics of both subsonic and supersonic flows are mixed. That you have regions of subsonic as well as supersonic flows. And there are some points where the flow is subsonic, and then some points where the flow is supersonic. But when you are increasing the free stream velocity over, let's say, a curved surface, let's say the curved surface of an airfoil, the curve of the aerofoil will rate the flow more, such that the velocity at some point there is higher than the free stream velocity. So if the free stream Mach number is already around speed of sound, then that means at some point around the body, when the flow has been accelerated more, the local number might just be 1 or greater than 1. That means you have some pocket of supersonic flow somewhere, even though the rest of the flow field might be subsonic. This kind of flow field is called a transonic flow field. And increase the Mach number further, but still you have this kind of flow too. You have a shock. You know what shock means as we go on. But just consider it as a discontinuity in the flow, at which the flow properties vary rapidly. So you have the local number varies from above 1 to less than 1. That means the flow, the region of flow directly behind a normal shock wave, is subsonic. So now supersonic flow coming, you have subsonic and you have supersonic all around. So it's a mixed flow, subsonic plus supersonic. So you have the transonic flow regime. The transonic flow implies one in which at every point in the flow field, the local Mach number to be greater than 1, just like we have in figure 1.3d. At every point in this flow field, Mach number is greater than 1. These are oblique shock waves. You know what they are later better. So now oblique shock waves, the flow across the oblique shock wave leaves us still supersonic after the shock wave. So the frequency Mach number for me is supersonic, and the Mach number after the shock wave is also still supersonic. Then flow is one in which the Mach number is greater than 1 everywhere in the flow field. And the speed of the flow is so high enough that the molecules of the have started dissociating and ionizing. And I do remember what dissociation and ionization means. It just means, let's say, for instance, it's of course the flow of air. Air is majorly nitrogen, so you have N2 N2 molecules in air. By the time you start having the speed to be so great so that the N2 molecules are dissociating into the individual atoms, then you're talking about a hypersonic flow. At this point, you can make assumptions of perfect gas or isentropic flows or all that anymore. So you have a hypersonic flow. It is not, there is usually not a clear boundary which we can determine when you have a hypersonic flow. One might say that okay, when the local Mach number or the free stream Mach number is greater than 5, then you have hypersonic flow. Really, this depends on some physics of the flow, the body geometry. So the correct description of a hypersonic flow is a supersonic flow in which the free Mach number is high enough for dissociation, ionization of the gas molecules in the flow to have chance effects in the flow field. Already we see that high-speed flows then have a lot to do with transfer of energy, because we talked about the temperature increasing and decreasing and all that. So if high-speed flows, high energy flows, then we need to be talking about thermodynamics, which is a science of, thermodynamics is a science of which centers on this study of energy. So in gas, in thermodynamics, we usually talk of a perfect gas, and here we continue talking about it. The perfect is just one in which the intermolecular forces have been neglected. Just like when we started the lecture, I was trying to what a mixed droplet contains. I heard it contains so many molecules. So those molecules we were talking about have intermolecular forces in between them, and the interfaces are such that when the molecules are together, they tend to repel one another, but when they are at a distance to one another, they tend to attract themselves. So that's the molecular forces are there. Sometimes it's just easier to negate the effect of such intermolecular forces of repulsion and attraction, make engineering calculations easier. So when we neglect effects of intermolecular forces in which particular gases, of a perfect gas. Most flow applications that we'll be considering in high-speed aerodynamics, compressible flows, the temperatures and pressures are really valued such that the assumption of the perfect gas is valid. The equation of state for a perfect gas is the product of pressure and the volume is equal to RT, where R is 1.8 is the universal gas constant. And C, if note that of course B is the reciprocal of density, we see the famous way the equation of state is that P equals to rho RT. There are how other ways you can or the of state can be stated when equation 1.10 to 1.15. We need to also recall the concept of internal energy and enthalpy. Energy is the summation of the constituent energies of its individual molecules and particles. due to random motion and vibration. When you we can go back to our app, and in the then we see what can happen. We see that the electrons are in constant motion around the nucleus. And for instance, the water molecule here is moving and vibrating some along with the electrons moving around. So for them to be moving, they must possess some kind of energy. So the energy of a gas is just the summation of all these constituent energies, all the particles it contains have. So the energies, the vibrational energies, the energy they possess to be moving around, that is the kinetic energy, and all you have to think about the potential energy and all that. That is the internal energy of a gas. Then we have enthalpy. So if the particles of the gas, which we call the system, are moving around affably in their state of maximum, so that means there can be no other gradient of temperature or pressure in the flow, then the system to be in equilibrium. Because once there is some gradient of temperature or pressure, there will be movement to cover for the pressure variation or the temperature variation, or everything is already in the state of maximum disorder, then the system equilibrium. So for equilibrium system of real gases, we also define the enthalpy to be the summation of the internal energy and then the product of and volume. Here, energy is usually a function of temperature, internal energy E is the temperature and volume of the gas, and of course, once E is a function of temperature and volume of the gas, it can be that enthalpy would be a function of temperature as well as pressure of the gas. But if chemically reacting, we can always ignore intermolecular forces, and then the system is now as a thermally perfect gas. Thermally gas, where energy E and enthalpy are functions of temperature only, and then the specific heats at constant volume and pressure CV and CP are functions of temperature only. So when we have neglected the effects of intermolecular forces, we are talking about a perfect gas, but the internal energy and the enthalpy are still functions of temperature. So we are talking about a thermally perfect gas. Then we can define the specific heat at constant volume. Specific heat is just the amount of heat that needs to be added by use to raise the temperature of the gas by a unit at constant volumes. So the E, the internal energy of the gas, is equal to CV dt, where CV for a thermally perfect gas is a form of temperature alone, and likewise the H for CP dt. So the of CV and CP is associated with the vibrational and electronic motion of the particles, such as what I showed with the NASA app. Then heats are constant. That means CPU are not functions of temperature, they are not varying with temperature. Then the system is called a calorically perfect gas. Calorically perfect gas. E is just equal to CVT and H is equal to CPT. You know that in most compressor flow applications, the of a calorically perfect gas is in order. The temperatures are not as high enough as to make CV and CP functions of the temperature. So we can assume a calorically perfect gas on the temperature is too high enough, CV and CP to vary with temperature. Then we can define R to be the difference between CP and CV. For H delta T and CV is the E delta at constant volume, CP at constant pressure. For equation 1.20, we can manipulate it to have this expression for CP and that expression for CV. For instance, divide through by P, we have 1 minus CV over CP equals R. And then we now define the ratio of the specific heat to be gamma. We can directly get expressions for CV or CP. Usually gamma is equal to 1.4 for air standard conditions. And then we got the first law of thermodynamics, which is embodied in equation 1.24, that the transfer the system boundary by maybe the reduction of thermal conduction, the work on the system by the surroundings is equal to change in internal energy of the system. That's thermodynamics. And we note that there can be various processes through which energy might be transferred the system and the surrounding. We are saying it might be due to radiation or thermal conduction or any kind of other means. There can be various ways which work be extracted or on the system too. And that's why we have partial derivatives here, because these are dependent on the that brings us energy transfer. But this is a total derivative, because state E intensity is a state variable. No matter, it does depend on the process. So if the process increases the internal energy, or if it decreases the internal energy, it's dependent on the process that comes about. That's why it's the E. So and then define a adiabatic process to be one in which no heat is added or taken away from the system. A reverse process in which no dissipative phenomena occur, and such dissipative phenomena can be in form of viscosity, thermal conductivity, or motion. So all these dissipative phenomena occur in the process. We are talking about a reversible process, and that the process, the next state of the process can all be covered because nothing has been dissipated. That means if you want to go from state 1 to state 2, state 1 to state 2, you can always go back from state 2 to state 1 because everything has been conserved. And if you have that, then you have a reversible process. So a process which are both adiabatic and reversible, is called isentropic process. If no heat is added or taken away, if all the energy of the flow is conserved, there is dissipation of the energy, then the entropy of the flow is going to be conserved too. That means the entropy at state 1 is just going to be equal to the entropy at state 2, and then the flow, the process of flow will be called isentropic process. For instance, it can be shown in most thermodynamic feature that the work done is just equal to negative PdV. So the incremental change in specific volume due to the displacement of the boundary of the system. So can rewrite the statement of the first law of thermodynamics to be del Q minus PdV equals to E. Just substituted minus dV for the W there. If we go on to as the process is adiabatic as well, then the whole process is isentropic, and then we can go on to get entropic relations. Thermodynamics introduces the concept of entropy, and entropy is just the degree of suddenness in the system. Entropy is usually used to get the direction in which a thermodynamic process is going to occur. And A is defined such that the change in it, the S, is equal to the change in heat added reversibly to the system, or taken away reversibly to the system, the temperature of such transfer. So in an alternate form, you can also define it as the S equals the Q over T plus the FE reversibility, because it is, we know from physical experience that always some form of irreversibility within the system, and always some form of dissipation of the energy of the flow or of the fluid when a process has just gone on. You are always, for instance, always going to have viscosity come there, and viscosity always dissipates the energy that a system has. So that is what gives rise to, or that is what makes us be able to write entropy in this form in equation 1.26. The S irreversibility to be greater or equal to 0. If we would have 100% process or a percent reversible process where the circuit, for instance, is not there, then the S irreversibility is just going to be equal to 0. But like I just said, processes almost always increase the entropy because of irreversibilities in them. So the S irreversibility is equal to 0. So that the S is that or equal to del Q over C. If we go on to that, if the S equal the S greater or equal to del Q over C, that means we can find the answer for del Q in this equation. Del Q is just going to be equal to C, going to be equal, I think it's going to be less or equal to C D. So that's a way to calculate entropy. If we put we call it let me switch my camera. We call that before we had the plus DE. We note for a reversible process, the U is equal to PdV. The plot P equals DE. Nothing that del Q that S is or equal to over T. And now I'm going to assume that the process is also adiabatic. The source is reversible, so that the S is to we're just going to take sign from the equation that we are going to say it implies that the value C ds no blurring I think it's so Q yes, we can put this then in place for in our equation so that we have TDS minus PD equals DE. But then we get that H equals E plus V, that is the NLP. Differentiate this, we have the E equals E P the P the V. So all this to that side, we have the H minus V the P minus the equal E. And then we can take and put into this one. CDS PdV equals DH minus P minus PdV. So minus PdV can go out, and then we have CDS equals D minus VD. So we have an equation with which we can directly calculate our entropy, given that we know the temperature, the enthalpy variation, the volume, and the pressure change. So we have equation 1.32, and note that for a fairly perfect gas, we have the H to be equal to Cp dt, which is to the which we just derived. And when we do that, we have equation 1.33. We do that, and then we divide through by t, we have equation 1.33. Then now the way to treat this point of the equation, that is, in order to be able to do the integration, we need to have this portion of the equation of the equation function in the p. In p, we have it as a function of p. Sorry. So if the perfect gas equation of state, not PV equals RT, we can find an expression for V over T, just R over P. So when we substitute that into the equation, we have equation 1.34, where the S is equal to Cp dt over T, R dt over T. At least we have the variables separated, and we can take the integration, we can perform the integration from a state to another. So to calculate the entropy change when the process has just gone on, we just integrate, and then we have to minus 1, as the next one was the initial state, and then S2 the final state. Then you can of dt over T minus R in P over P1. We have not taken Cp out here because we are still assuming a thermally perfect gas. In Cp is supposed to be a function of temperature. So that 1.35 holds for a thermally perfect gas. But if we assume we assume a calorically perfect gas where Cp is a constant with temperature, that means Cp can just go out of the integral sign, and then we evaluate this integral, which is in T. That means minus S1 equals Cp in T2 over T1 minus R in P2 over P1. Similar thing, then dE is equal to Cv dt on our previous equation, our energy equation. Then we have a similar expression for the calculation of entropy in equation 1.37. For entropic process, we are saying that the change in M is equal to 0. That means S1 is just equal to S2. And the equations which we've just been able to now should be equal to 0. So if we take the first one and equate it to 0, we have P in T2 over T1 minus R in P2 over P1 is 0. Thus we can equate one part equation to the other, and then do that. Then when we have done that, we note that Cp over R is equal to gamma over gamma minus 1. We do that full that for an isentropic process, the ratio of the pressure is the ratio of the temperature raised by gamma over gamma minus 1. We can same thing for the second equation for the calculation of entropy, and then by the fact that the ratio of the densities is equal to the ratio of temperatures raised to power 1 over gamma minus 1. It can be combined. These two, equations 1.39 and 1.40 can be combined to can be combined to get equation 1.43. The equation governs isentropic flows. Note the assumptions which we have made here. We have made the assumption that the flow or the process is reversible and that it is adiabatic. And if it is reversible and if it is adiabatic, there will be change in entropy. So it's an entropic flow. So if you have a process where you can assume it to be isentropic, then this relation be will be but let's this though. We know that viscosity is always present in nature. So in the flow of any kind of fluid, we expect to have viscosity. And sometimes we might have some energy being taken away from the fluid, or some energy being put into the fluid. How then or when exactly can we have the isentropic maybe just to meet also. But then we know that when the flow over a body, there's usually a thin region attached to the body where the effects of viscosity, thermal conductivity, and mass diffusion is highest or greatest. So that's the boundary layer. That means the outside the boundary layer is usually we can usually be considered to be reversible without loss of activity. And then if there is no mechanism to directly be heating the flow, like consider the flow over the wing of an aircraft. If there is no mechanism to directly be heating the flow or taking away heat from, then we can assume the flow to be adiabatic. So adiabatic plus reversible just means isentropic. That flow out of the boundary layer is safely assumed to be entropic, and in this case, the isentropic relations embodied in equation 1.43 is valid. To recall that the aerodynamic forces on a body are due to forces. The distribution on the body and shear stress distribution on the body. We therefore note that an integration of the pressure distribution and then distribution over the body surface gives us the aerodynamic force on the. Once we have the aerodynamic force on the body, like say for here, we can resolve it into the components perpendicular to the free stream, that is the lift, and the components parallel to the free stream, that is the drag. We call this because the whole concept of aerodynamics, the study of aerodynamics, is just to be able to predict the forces that the motion of air over them, or so that the motion of air over bodies create. So that's just what we are concerned about. So in compressible flows too, you want to see the effect of compressible flows around bodies. You want to be able to predict pressure variation and then the stress variation, in order that we are able to now integrate such pressure distribution and shear stress distributions around the body and get the forces of interest. Kind of summary, mini summary, we've seen that compressibility is defined as the fractional change in volume over change in pressure, and then we can also define it in terms of density. When we do that, we can find an expression for the fractional change in density to tau times the P. And we know that compressible flows partial flows at Mach from 0.8 to infinity. We know that we stated earlier on that usually when the flow Mach number is greater than 0.3, then the compressibility effects are quite not the then we factor them into any kind of condition. And then speed flows are compressible flows and they are high energy flows. That means the thermodynamics is important for the study of compressible flows. Let's then look at the integral forms of the conservation equations for in flows. To predict the distribution of flow properties, we need to we need to kind of like write the word in get the equations in which the word is written, because the pressures are related to the velocity, to the temperature, and some functions. So this uh, to now predict the function of these properties, um, we need to share the fact that the word is written in mathematics. So they are taken, or usually been taken, to get these functions, or to get the way properties relate to one another, and said in the bullets 1, 2, 3. Firstly, choose the appropriate fundamental physical principle from the laws of nature. First, of course, is mass is conserved. Second is conservation of momentum. Third is conservation of energy. Then we apply the physical principles to suitable model of the flow. We know here that it is important to get a suitable model of the flow. For a fluid which can flow, you don't have a definite shape. You don't have a rigid shape. So there's some kind of model that we use to define the motion of fluids. Then the motion of fluids is not as trivial as one can think. Of solid objects can be. So from the compressive aerodynamics class, we know that the approaches which are the final control volume approach, the infinitesimal fluid element approach, and the molecular approach. The first approach is final control volume approach, and then the infinitesimal fluid element approach are by far the most widely used. But you do the molecular approach, um, the laws of fundamental physical principles are used on molecules, and then the integral effect on the whole volume of gas is led by some kind of statistical means. So for the final control volume approach, a control volume is run within the flow field, and then the physical principles or the physics are then analyze the flow inside the control volume. For the fluid element approach, a fluid just like the mist droplet, or smaller than the mist droplet that we were talking about, we do that, and then the physical principles, laws of nature, will now be used to analyze its motion. Either the three approaches should result in the same results, because of course these approaches are trying to model the same thing. However, they can have varying expect that depending on the approach, the result may be more apt than others. Then you do appropriate fundamental physical principle, applying it to applying the physical principle to the suitable model is to derive the mathematical equations governing the fluid flow. We already saw this in compressive aerodynamics anyway. So we know that when we did what was said to be done in 1 and 2, we got the continuity equation, the momentum equation, and then the energy equation. This is stated here for a kind of review. If comfortable enough with these equations stage, you are advised to go back and then look at them more. Continuity equation just means mass can either created or destroyed. Since the mass flow into the control volume should be the time rate of change of mass inside the control volume. And then term equation, we know that the Newton's second law says F equals ma. That means if you have the summation of forces, you'll be able to the moment, the rate, time rate of change of momentum of the fluid. So this can change of the momentum of the fluid, either if it's the control volume as these are triple integrals anyway. It can also mean for a fluid element when we try to this the integral equation into the partial differential equations. And then the equation is just a statement of the first law of aerodynamics, of thermodynamics, the heat and then should be equal to the change in heat, change in work plus the change in work should be equal to the change in internal energy of the fluid. Yes, we need incompressible flows, high-speed flows. We deal with one-dimensional flows a lot. So we need to look at what one-dimensional flows mean. We hear that shock waves dominate the supersonic flows, and like I said before, a shock wave is just a region of discontinuity in the fluid. True flow properties change drastically. We can have a detached normal shock wave. That normal shock wave, such as the one depicted in figure 3.1a, is called bow shock. A bow shock because it looks like a bow. It's like a bow, the arrow and bow thing. That is a bow shock, and it was in most bodies in supersonic flows, and it's usually detached from the body. But most bodies, like that which is the figure 3.2b, so 1b, you have attached oblique shock, oblique, and that's because the shock wave has some kind of angle of inclination relative to the body. So that's why they are called oblique shock waves. About them can be seen to have to be a question of normal and oblique shock waves, because at the point of the is near normal as the flow, as we move away from the nose of the body, we have it back. So it's like a combination of oblique as well as bow shock. Normal wave is of course is perpendicular to the free stream direction as illustrated in figure 3. Through the normal shock wave reduces the velocity of the flow. That Mach number the flow from flows from one station here to station 2, then through the shock wave there, a shock wave, then the Mach number would have reduced to below 1, as it goes from supersonic to subsonic, of the velocity will have reduced, the density will increase, temperature will have increased, and the pressure will have increased. Normal waves are very good examples of one-dimensional flows because the change in the flow properties is usually just in one direction. So that we call with very good examples of one-dimensional flows. Oblique or two-dimensional phenomena. We can define a quasi one-dimensional flow. Which the one-dimensional flow, that means it is in real life not a one-dimensional flow, but because of some assumptions, we can now model it as a one-dimensional flow. So, for instance, the flow through the element or like a cylinder here will be a one-dimensional flow because then A is constant, the area of the cylinder is constant, and the variation of the properties is due to variation on the x-axis. But when the area will also be varying with respect to x, that means as we move from one portion to the other, the area is varying, but the variation is modest, it's not abrupt, it's not sudden. Then the variation of flow properties can also be thought to be functions of the coordinate space, one coordinate the x-axis. So you assume that the flow properties are still functions of just one dimension only, just because the area of the bounding the flow is mostly varying in that direction. Then you have a quasi one-dimensional flow. So we are now trying to use the express continuity, momentum, and energy equations on the one-dimensional flows to get the relations that govern one-dimensional flows. So now we will try to derive the one-dimensional flow equations. We use figure 3.5. We get the flow through the dead one-dimensional region, which is representative of the normal shock wave. The normal shock wave, that is the part of the power shock wave, which is just perpendicular to the flow direction. That is, like showed before. Showed before. Let's say you're playing and you have a shock, and then the directions there. So that portion shock wave, where if you blow it out, you see something like this, and if it's just perpendicular, that's called the normal shock wave. So we just assume a flow there, and then to draw a volume around shock wave, and on control volume we are going to use the equations in the graph form. So properties are a function of x change from state 1 to state 2. So in order to calculate the changes in the properties of the flows, the integral conservation equation is the rectangular control volume. The area of the rectangular control volume, that is the cross-sectional area, to be A, where is just this control volume, we are taking a unit depth in the slide. So with our analysis, we are going to make some assumptions, and some of the answers are that uniform flow on both sides, and also that if it is uniform, that U is not varying with height on both sides. That means we've taken a control volume small enough such that there is no variation on velocity in the vertical axis. It's just uniform x axis. And one of the assumptions is that stations 1 and 2 have equal areas, which is perpendicular to the flow. That area A equals the area A. Both areas are perpendicular to the flow. And then we are going to assume that the steady realization of these flow properties with time, and then to assume that the body forces are negligible. Some body forces are force of gravity, electromagnetic force, and all that. But here we are going to assume that there is no, usually of course there will be some for gravity, but now we're going to assume the effect of such force is negligible on the flow in the x direction. And before we proceed, I think you have a drawn, the elemental vector, the unit vector is pointing out perpendicular to this. So that's the unit vector at ends on this top face of the fluid element is always pointing up. Yeah, and over here it will be pointing to the right. Over here it will be pointing to that, and here it will be pointing. That is, it's always pointing out of the outwards from the surface. If it is bounding some volume, then the elemental unit vector is always going to be pointing of the volume. So going forward, invoke the continuity equation. Because assuming steady flow, this part of the equation goes to 0. So we are going to get with the integral of the flow rate is equal to 0. That just means that the inflow is equal to the outflow. So in order to get the one-dimensional equation, we need to evaluate this on the surfaces of the control volume drawn. So and then we need the value is dotting the elemental surface vector. We have the dot product of two vectors. I want you to record recall that the dot product of two vectors that are perpendicular to one another is equal to 0. So if the two vectors are parallel to one another, you just have to multiply the magnitude of vectors in the direction of interest by one another. So dot product. So you still record the dot product on the curve volume. With additional which analyze, I think this can this one. So the control volume around it. And you that you recall that the elemental unit vector is always pointing out of the control volume. In this space, the elemental unit vector is pointing to the left. It's pointed on that it is pointing to the here it was and upwards. So the velocity is coming this way, u is in the x direction, and it's going in that direction. V. The flow is uniform in the x direction. We don't have any component of the velocity coming out from here. So v, which is a component of velocity in y is equal to 0 there, and then v equals 0 there as well. We try to now do the into rho v dot ds, where e and ds are quantities. Yeah. That is A. On this space, this vector ds is pointing to a direction to where u is going. Dot product then will give us a negative value. So that minus rho u a. So is there to serve the purpose of showing us that this and u are in the same direction, not in the direction. So we have an inflow, negative sign. And this space, the x and are in the same direction. So we have rho u a, rho a, and look at this space. The v is coming out here, and v is in that direction. That means the s and v are perpendicular. Yeah, so that means the dot product will be 0 on this face as well as on that face, because v, which it components only in the x direction, is perpendicular to d on these faces. So the dot product of v and everything will be equal to zero. It just means there's no outflow or inflow from the upper and lower boundaries. The flow is just in that direction. So it should be equal to zero. And it just tells us that rho U1 equals rho 2 U2 as the continuity equation for dimensional flow. So we know the equation for one-dimensional flows. So integral form of the momentum equation is given as if we study flow and we neglect body forces, and this part goes to zero and that part also goes to zero. We are just left with the momentum flow, net flow in out of the net momentum flow in to the quantum is just equal to the pressure forces. So we go to integral. Note that the pressure, of course, is always acting inwards to a given surface. The pressure acting inwards to a given surface. If I switch to the camera and look at that again. Yeah. This is a question of interest now. Of the yes into ds. We know always act inwards to a given surface. Here, look at the control volume drawn again here. On F, pressure is acting inwards, acting inwards at given point in time. The direction of the source unit of gas is in opposite to the direction of the pressure forces on all sheets. So if those pressure is always inwards, so they're in opposite direction. So while trying to exit these integrals on the faces, one has to take that into consideration. And this in the bracket is just going to be the same way we evaluated the one here. Note that this is a vector equation which ends in both x and y, and z direction. But since we are considering only one flow, we are going to be taking the x component of this. That means during flows, we are taking v s component of the loss in the x direction, and this is the the pressure we will be considering is just in the x direction. So, sorry, the correct way to have written is PS is subscript x, just to show that gives us a pressure force in the x direction. When we are on both faces, we come with this equation here, refers to 3.5 P1 plus rho1 U1 squared equals P2 plus rho2 U2 squared. And this is a statement of the conservation of momentum for the one-dimensional flow. Then we'll go on to the equation for one-dimensional flows. The general statement, general mathematical statement in the integral form for the energy equation there. We let this part here let be equal to, and let it be geometric rate of heat addition to the control volume. It's symmetric phenomenon. So let's just denote it with Q dot, capital U dot. For steady with no body forces, then that means this is going to be equal to 0 and part is equal to 0. Let's left then with equation 3 point. All we have to do now is to also evaluate this equation on the volume drawn around the one-dimensional discontinuity in the flow. So, we need to then evaluate this integral. We should note then that V dot ds, V dot ds will follow the same kind of integrating this on the two faces will follow the same kind of procedure. We're trying to integrate integral of rho v ds on the faces and see for this part of the equation. So what is done, and it's nice if you tried it. This equation here, and let through by A. When you by A and you rearrange, you have equation 3.7. You can also go further by dividing this equation by rho1 U1. And dividing this part is the left hand side by rho1 U1 and left hand side by rho2 U2. In this we have 3.8. You should note here that then rho1 U1 is a mass flow, because that is just 2 times velocity times the area. So you have volumetric rate of heat addition, the mass rate, Q, this is Q over T, M over T, and Q over T, Q over T, multiply C over M. It is, and then you have Q over M. M is just the total heat by the mass of the system, and this is just telling you that we have specific added the system, that is the total heat per unit mass. So that means we can make that substitution into the equation here. And then also note that rho equation, um, rho, the density is the reciprocal of the specific volume. That's over in place of our rho 1, we can have P1, V1, and over here as well, in place of P2, rho 2, we can have P2, V2. We'll have that. Then we can also record that H, which is the peak enthalpy, is equal to E plus PV. That means we can make the substitution of H to equal these two equations. So we are going to come up with equation 3.9, which is a statement of the conversion energy for one-dimensional flows. There is the enthalpy plus the specific enthalpy at the station plus specific kinetic energy at the inflow station plus the specific heat addition is equal to the specific enthalpy plus specific kinetic energy at the outflow station. That the energy is so the continuity, the momentum, and then the energy equations for one-dimensional fluids. It should take some time to redigest the content of this slide, which talks about the speed of sound and Mach number. So then, if you consider sound wave depicted in figure 3.6, and let it be moving with velocity a through the gas, the changes across the sound wave can also be thought of as a one-dimensional flow. So the equations, the one-dimensional flow equations, which we've obtained in the can be applied to the flow across the sound wave. So before we define the flow station in front of the sound wave to be station 1, and then the station of the behind the sound wave to be station 2. The sound wave is moving into the fluid with the speed of, if we want to now shift the reference to be on the wavefront, it will be the inflow from station 1 is moving to the sound wave at speed A, and the flow leaving it is as if it's moving with some shift velocity of the changes within the sound wave. So we just represent the change in velocity by dA, so that speed of the flow behind the sound wave is A plus dA. If T, rho, and T are the conditions of the flow before crossing through the sound wave, due to the slight changes counters while passing through the sound wave, we have some the P, the rho, and the T added to the pressure, density, and temperature. So I mentioned that the flow through the sound wave is one-dimensional. So we can just use the one-dimensional flow equations to the sound wave. We can just try to draw the control volume and the sound wave, and use the continuity equation and then the momentum equation later. If we use the continuity equation, we note that rho u1 should be equal to U2. rho is there, and then um, at this point should be equal to is in the x direction. We have rho A equal the pressure, the density at station 2 is rho plus the rho. Then the speed here is A plus the A. And then note that these within the changes in flow properties is going through the sound wave. Very, very small change because the sound wave is a very, very weak wave. So that the changes, the A, the P, the rho, the T are really, really very small. So that when we expand out this product, that the rho, the A will be very, very small because it's just a product of something that is extremely small with something that is extremely small. So this is just going to be infinitesimally small and can be ignored. This part we can cancel out that part of the equation. Essentially have the speed of sound A to be equal to minus the A, the P, with that used later. So from the continuity equation we have gotten equal 3.11, we go on to the dimensional momentum equation of the sound wave. Same as before, P plus rho A squared, because speed plus the P plus, which is the pressure at station 2 behind the sound wave, and the then at station 2, and that's square of the pitch behind the sound wave. Because of differentials as before, equation 1 2 becomes the P equals that. We can now use this and insert it into the equation we got for this the equation we got on the previous slide, and it's that the A equals that. Sorry, from 3.13 we can get 3.14, and then we can substitute 3.14 into the equation we got on the previous slide. One way we find that A squared equals the P over the rho. So this is good enough place to stop and then have over all that has been talked about today. When you do that, I want you to also next slide. This one, that one, and this one as well. So in lectures, I'll be starting from, if you go at this, but I'll be starting from slide 37 in the next lectures. So, and remember to send me your feedback, comments, and questions. Thank you.